going to assume that you can hear me online. Please raise your hand if you can. I'm Dhruv. I am going to give a talk about CN, which is a separation logic and refinement type system for C. I apologize if you've seen a news talk last week, because this is essentially going to be similar slides and a more condensed version of that. But also feel free to ask any questions that you didn't get the chance to ask Neil, especially when it relates to inference, to resource manipulation, or the formalization. I was handling the proof side of things and making sure that all the inference stuff that Christopher and Thomas were implementing was somehow justifiable mathematically. So that's a little bit of bookkeeping. Right. So CN is a separation logic type system for C, and we're doing this because we'd like to verify a hypervisor, specifically protected KVM, which is being built by Google to deploy on Android. The basic idea being that hardware vendors can essentially supply a different operating system for their modules, and you have separation between the multiple operating systems on your phone, so that, let's say your camera module can't go over and listen to your microphone, and your Wi-Fi module can't steal data from, let's say, where your password is stored. And so this is a good target for verification for a few reasons. One is that they very much care that this is secure, so that's nice. And the second is that reasonably small. It's about C, which is quite well written, a simple locking discipline, and some inline assembly. And the idea is that they want this to be well understood so that there aren't any subtle bugs. So in the first pass, at least, they are trying to make sure that it is just simple, easy to understand, but reasonably performant as well.
What proportion of that NK is C?
I don't have stats off the head of the head.
Most it is C. Maybe there's 1,000 lines of assembly. But the thing about the assembly is not really that it's assembly, it's that it's assembly that you can't possibly write in C. It's DLB maintenance instructions and exception vector stuff that Angus was talking about. It's system state manipulation.
So with CN, what we'd like to do is not just do one verification, but basically create an artifact which, in an ideal situation, the developers can maintain themselves perhaps with a little bit of help from experts, but not have a team of PhD students like myself and Angus constantly working on this until the end of time. The kind of aspirational goal is they should be able to understand, read, write, review the invariants that they write for themselves, and hopefully you, in an ideal world, you kind of push a button, do a little bit of extra proof work, but hopefully not too much, and maintain the proof as you make changes in the operating system, which, this is a commercial piece of software, it needs to be updated all the time. However, as willing and these motivated as these kernel developers are, you can't expect them to learn separation logic or proof of systems. Although I know that Thomas has mentioned that at NICTA they managed to get some mileage out of doing that. That potentially is just too slow for industry, even if it is possible. And you also can't expect them to radically into their workflows. So we would like something that ideally integrates into the build system. So this is something, for example, that Peter heard and his Infer team really understood at Facebook, which was like, as much as these theoretical tools that we have are amazing, if you can't get them into the daily build, it's just not feasible. So that's kind of some of the reasons for which we think that adding fancy types to C might be more realistic approach to handling this verification. However, fancy, yes?
Just a remark, the daily build was not ambitious enough.
or Peter O'Hearn on Facebook, they wanted every commit, right?
Oh, yes.
Illegal is already too late.
That's fair. That's fair. But yes, exactly. That sort of with every commit, and then that sort of responsiveness. Like we'll show a screenshot later where we actually want to get into the IDE and just say, like, this is where the error is and this is why. But to do this sort of kind of fancy title verification, we need to satisfy those some constraints. We can't spin forever. We need to have it decidable. We need to have it predictable. Randomly reordering constraints shouldn't make a randomly reordering, let's say, types, predicates, whatever, shouldn't make verification go through in one case and get stuck in another. And the errors need to be explainable to C programmers in a context that they understand. And as you see, these are also aspirational, but we have good ideas and I think potentially good ideas on how we can tackle each of these. So just some concrete syntax. This is a little bit out of date. It's using the annotation syntax. The Google developers prefer magic comments, so we've now changed it to magic comments. We have precondition, which is the requires clause. And all that one's saying is that for every pointer in this range, we have a byte. And the postcondition simply states that the byte is 0 in that range. The ensures that 2 equals 2 at start is actually no longer necessary. That was a minor technical implementation detail that I was speaking through, which we have since then fixed. And we require that users annotate loops with loops invariant. And we do the same. Well, the pre and post conditions, they serve as a form of essentially documentation, even if it is potentially verbose. And loop invariants are just hard to infer. Like that's an open research problem. So we can deal with that by doing that. Yes.
So what you've shown here is basically a shape analysis verification. There's some byte there, and these bytes are 0. And the fact that there's some byte there is already information that memory is allocated.
Yes.
And if it's separation logic, there's even more information, which is that, here's the footprint and outside of that, right? But it doesn't say what the value of the byte is. So that's what I mean by it's shape analysis. It doesn't go as far as functional correctness verification. Say which byte it is, how that byte at this address relates to what the program is supposed to be doing.
Well, that's in the post condition. It means they're all zeros.
This function just doesn't care about values.
I see.
Page
So-
vary function. It's 0.
So the ambition for this project really is functional correctness verification. Okay. All right.
And so in this example, it says clear page underscore 4096 bytes, which is a single page size in PKPM. And we're also doing a little bit of predicate definition manipulation, packing and unpacking, what this means. Again, this is a slightly older example, so not sure this is actually, in this case, I don't think it would be necessary anymore. And as mentioned earlier, this is something that I am proud to say that I managed to hack together, which is a prototype. It says the word prototype quite heavily. Implementation of an LSP client and LSP protocol for CM. And what that does is it will give you some location information and it will generate this HTML file with a counterexample state in which the preconditioned broken post conditions are insufficient for the program's set of behaviors. Here it's signed integer arithmetic ortho. And the way that it says that is that expression S0 can have the value of maxint. And so therefore it can overflow. These are automatically generated variables that we want to replace with actual programming expressions fairly. This has been one of the bugbears in developing this tool is the usability of the output state. It's barely good enough for research users, so we would not show that to you just yet. We have several problems with this goal that we're trying to achieve. One is just C, and I think everyone here is familiar with all the weirdness in C, such as scoping, control structures, variables. Maybe just a word on this, which probably is the toughest one when you think about verifying C, is not only are variables mutable, but you can take the address of them and you can initialize them later from where you declare them. And designing a type system which takes this into account would just be a pain. So, not to mention all the undefined and underspecified behavior that is in the C stack. And so, yes.
How much of this weirdness is actually used in PKP?
People assign the variables on almost every line.
Apart from that, yes, the control structures are reasonable. They obviously take addresses of variables, and it's mostly the compiler which will. Obviously, the programmers are trying to avoid the UV, but the specification is long as it's in prose and it's ambiguous in some places. So try as hard as they might. No human can be reasonably expected to remember all the undefined behaviors and then program against them defensively. So having a tool help with that is really helpful. Yes.
So can I make a remark about designing a type system for this?
Yes.
CPP 2011 approximately, Joey Dodds and mostly sound type system for C program verification. And what mostly sound means is it automates most of the verification conditions have to do with all these weird conversions and leaves only the residual proof goals to do in code. And Joey Dodds' name appeared on various slides last week, but now got a lot of times on. So yeah. This is a way to again help computationally automate a lot of the sort of easy side conditions by making something that almost looks like a type system.
Yeah. And what was your experience in working on that type system? Is it more complicated, or like what was the complexity of that?
Well, choice one is don't have a type system. You don't need it. It's got an operational semantics. You can make a program logic that incorporates all the side conditions, generate all the side conditions, solve them automatically with technical proofs and code. And the purpose was just computationally analyze the deep embedded C expression, calculate in a sound way that, I've computed that I don't need to admit all these side conditions and I only need to admit those.
So
It's not what you're doing.
Yes. Right. C program that does, sign integer arithmetic or shifting by a variable number of bits or by constant number of bits. You'll see all sorts of side conditions that you won't see because it is computationally calculated in a way, improved sound way.
You said this was CPP 2011?
Approximately 20.
Yeah, we'll take a look because, these are all conditions we end up discharging. And, if you make the SMT problem somewhat, I think it's going to run faster.
Yeah. So, or you can, read the source code and read code now.
our approach is to use Cerberus. This is a composition of well-validated forms of semantics. And the nice thing about Cerberus is that it compiles to first-order functional language core. And the nice thing about this is that it makes things very explicit and very straightforward, such that some C code plus annotations goes through the Cerberus pipeline and ends up with some core with refinement and separation logic types. And this is where I very much was grateful for Cerberus, because this was an old version of my work where I was actually formally specifying the type system. And the reason I show this is not because it is complicated, but because it is simple. These are pretty much, this is a pure fragment of the typing rules, and the rules for if, let, pattern matching case are exactly what you expect from a first order functional language. And
these are Cerberus.
These are, yes, these are type rules over the serverless form.
And these are Dhruv and Neil refinement type rules over the serverless form language. So core itself, it's just a simple, straightforward first order language.
Yeah, and then we add fancy types on top of core instead of directly on top of C. And this makes things actually tractable and reasonably straightforward. It turns a difficult proof into a tedious proof, which that's a way in programming language theory, I think. So, and the judgment is relatively straightforward as well. So we have core variables, which are variables from the core generation program. Logical or ghost variables, these are the things that we use to keep track of the ghost state, and the constraints of the constraint context. The B there stands for base type, and these are the simple types from the core language, whereas the P there is predicates on the value of that type, and the T is just the core term type. And so with this, we now come to our second hurdle, which is quantifiers. And we want quantifiers. Quantifiers are very good for expressing variance and so forth. But also, as you can see, if we want predictability, we want termination. If we want termination, we want a decidable SMT fragment. And if we want a decidable SMT fragment, we want to not have quantifiers. So we've got two goals or desires which are in tension there. And here's an example of this, where let's say f, I don't know, adds 1 to the function and then returns it or doubles it. And to express the specification, although it's relatively simple, there's already quantifiers in there. The way we get around this is by tying quantifiers for the for alls and the pi types to the pi type specifically being instantiated by the argument, and then sigma type is bound to the core program variable. And so when it comes to checking an assertion, we know that the core program variable is greater than or equal to 3 because it matches up with the sigma. Yeah. And this is essentially the good types discipline, and it ensures decidability.
Yes. Interesting fragments you look at. One that's using Title Verified.
Sorry, which type?
ID. Those site.
Yes. That's good to know. The other aspect of this is that, like, even without quantifiers, getting reasonable predictable performance, it's not just like, it's like decidability is just like this very, in some sense, a low baseline. We want not just decidability, but like the programmer should be able to type, wait for maybe some few seconds and get the result back. And so it's like there's a complexity that we don't formally state it as such. These seems to be reasonably straightforward as well.
Yeah, let me add something here. So that we've run into like sort of an interesting usability problem. So if you put in just a few refinement types, everything works really fast. And so that comes you to put in a few more and a few more, and then the performance gradually gets worse until it's sort of the worst you can tolerate. And so, you know, finding like making the slope a bit less slippery.
So what is the slowdown? Is it case analysis that you need to use when you do it?
It just seems to be something about SMT solvers.
Yeah,
More variables.
yeah.
There's a point at which it just goes
Yeah,
too slow.
yeah.
So you can only use one. So it might be-
Oh, in this case, it's fine.
Yeah.
Yeah, actually, Thomas has investigated like the causes of our slowdowns the most. I was saying that, you know, if there's just a few annotations, it's pretty quick. And so that tempts you to put in more and more until it's not such a great experience. You know, station. The problem is unexplained. where these issues come from. We need to talk a lot more concretely about what package. The front end syntax and the typing rules effectively elaborate the semantics of before, and there's some other details as well. And unfortunately, one of the problems is we don't end up with relatively concise SMT problems. I have the suspicion that what's actually going on isn't related to the scale, but specific things. But
Just hitting some gigs.
it's relatively easy to construct the kind of classic pattern to it if there's type disjunctions which force the solver to make some considering one cases. Where in fact it might be something common, but it still makes it. An instance of that problem is very easy to generate. That's to try and control it, but there are I don't have to like give you a precise answer. There are various issues. I suspect once we pick up enough of the superficial issues, we'll spot the real issues.
The third thing that we want to be able to do is enforce a resource usage discipline.
So can I ask one more question? The sound is breaking up a little bit, so maybe that was discussed already a little bit. But on the previous slide, when you do this specialization, does that mean that you have to verify each application of this piece of code separately? So it's kind of monomorphization, or can you keep the generalization and just instantiate different application sites differently?
So the F would be proved, the implementation of F would be proved against the spec, and that would be done once. And then at each call site, you have to prove the precondition, and then you assume the postcondition as that. But no, you don't have to do the, you don't have to re-verify F for each call site.
Okay.
So we'd like to enforce a resource usage discipline, but we need to do this in the context of hypervisor C. And we can't borrow tricks from, let's say, Rust, where you have an exclusive alias which guarantees ownership. And we also don't really want to ask programmers to explicitly pass around capabilities. That potentially might be too much noise for, at least simple operations like dereference a pointer. So we like to infer resource usage. And this problem becomes even more acute when we're talking about the swap function, which is primitive in Rust, but it's pretty standard in C, where we pull out ownership of the array and then we put it back in. And I don't go into this in the talk too much, but figuring out kind of what the algebra of the manipulations of resources that are allowed in the program was a significant part of the contributions of our work. And once you have the resource kind of algebra, the operations on the resources, then comes the work of proving that these operations are sensible or sound to do. And lastly, we have things like invariants that we want to express as predicates. And you'll notice there that there's an existential, and we just mentioned that we don't want quantifiers. And similarly, if we wanted to use a predicate in a function specification, we would also need quantifiers on the list argument access. So similar to the resources, though, we don't really want programmers to have to manipulate the ghost state and the ghost capabilities explicitly most of the time, let's say. It might be unrealistic to get them to automate it all the time, but most of the time, this would just be extra noise. And this violates the local typing discipline. And the solution is to divide predicates arguments into inputs and outputs. So for points to, it's actually pretty straightforward. And given that the points to is the kind of base level predicate, the the inputs and outputs work out quite nicely from there. And this will be familiar to some of you as a mode system from programming logic programming. This is how the modes work out. You can quantify it over Q existentially because it occurs as the output of a points to, and then you can use that as an input to a predicate later. However, I can speak from personal experience on this one. I used mode programming when I was playing around with some other verification tools. And initially, I just found it confusing. It's like, why does the question mark go here? Why does this predicate not work? One of, I think it was Neil's idea, which was, I thought, it's like, I finally understood modes after I saw this, which was referring or thinking about predicates in terms of a monad. And through these series of equivalences, you can now formulate a predicate in terms of an input and an output. And so with a little bit of a syntax reshuffle, you can then specify how to write predicates in this monadic style. And the nice benefit about this is one, no quantifiers, and two, your mode checking becomes your variable scoping. So it's like impossible to use Q as an input argument before you get it as an output. And this is the full mathematical translation of this, and it's actually not that complicated, which is another wonderful thing about it. We denote the semicolon here becomes a star. These two expressions are translated recursively, and the existential is just exactly what the binding is there. And so then you're able to refer to the output argument of the list predicate in the type because it is determined by the inputs. And so, yes?
If you're at the summary slide.
Yeah. So we have, we really restrict our logical constraints to the cycle fragment of SMD most of the time. We try and do these restricted predicates so that they're precise, so that we can infer the existentials and introduce logical variables without confusing programs too much. And hopefully have a understandable specification. The nice thing about this is that it also specifies how to trace the heap to dynamically check this. It's not necessarily limited to being useful only at static or compile time. You can potentially turn this into a program, although we leave that to future work. And so just one more thing about, we need escape hatches. This is just the truth of the situation to handle things like quantifier heavy reasoning and nonlinear arithmetic. And for that, we have a way of exporting our types from our grammar of pre and post conditions to and Thomas was the person who worked on that. So thank you very much for that, because that very much increases the confidence in which we can use our system. Because now all our quote unquote lemmas, which are simply C functions with an empty body, but just change types, are now verified elsewhere. So that's all for the talk. I'm slightly over, but I apologize. I'll take one or two questions and
So I have two questions, which are really the same question. First one is, when you have an escape hatch to talk like this, with some lemma to be proved in talk, then is the software engineer building the hypervisor going to maybe not prove that lemma in the first place, but maintain it as its statement changes as necessary?
yes.
And well, let me ask the second question, which is the same as the first question. Go back 2 slides. So here you are very properly relating the C function called length to a functional model in coq, which you note by 2 vertical bars on x's, but really it's the coq length function. So this is an example of a more general pattern where you prove a C program correct with respect to a functional model in coq, and then you prove the properties in coq of that functional model. For example, that length relates to list of hen with a plus sign, right? And so when your engineer changes the way that the C program implements that same functional model, there's not necessarily any clock work to be done by that engineer, just in your low-level program logic, separation logic. But when the software engineer changes the C program such that its functional model also needs to change, then other theorems need to be proved in Coq about the new functional model and how is that going to be maintained.
Yeah.
So I like the approach, but eventually those engineers are going to be learning Coq.
The idea is that, let's say, I think from a Google perspective, they'd rather hire one or two postdocs rather than a team of them for the rest of the community. But
Or one or two people with bachelor's degrees who learn Coq.
exactly.
Yeah.
Yes.
Right. Yes.
So this is the kind of the problem is such that you can't avoid this, but we are definitely doing our best to minimize it. And so if all the kernel devs need to know this, I think that's unreasonable. But if maybe one or two of them are able to do a little bit of this, then I think that's probably easier sum.
Okay. So the good news is
Yes.
we have discovered in several projects that it really is a different engineer who's proving the Coq theorems about the functional model than who is proving that the C program defines the functional model, and that separation looks great.
That's very good.
So yeah, that's the grand aspiration here is really possible. Having the entire verification being very predictable refinement something. So one has to view this as an experiment in pushing as much as one can into predictable setup. It's unclear how much will be pushable in just the subject.
Yes, we should.
Yes, thanks, Joe. Okay. Now we'll take